Our next speaker is Zhang from the ECE department here at IUSC.
Good afternoon, everyone. My name is Yang. I'm from fourth-year graduate student from ECE department, and my advisor is Professor Mark Hasegawa-Johnson. So for the next 20 minutes, let's shift our attention to the field of speech processing to take a look at an innovative probabilistic acoustic tube model that can potentially be applied to various speech processing tasks. First, let's look at the motivation of this work. To really understand the motivation, let's take a look at one of the most important approach in speech processing, and that is the model-based method. So the model-based method basically assumes there is a model for speech with some hidden variable of interest, and then the model characterized how the hidden variable generates the observed variable. So with this generative available, we can then, based on the observed variable, to infer the value of hidden variables. So this kind of model-based approach is very common in speech processing. For example, in pitch tracking, the hidden variable, of course, is pitch, and then the observed variable is autocorrelation function of the speech waveform. And more frequently, in speech recognition, the hidden variable is often the phone or the sound you're trying to make, and then the observed variable is the MFCC. Those of you who are not familiar with MFCC, it's basically a parameterization of speech waveform that's most indicative of the phone being said. This can be directly calculated from speech waveform. So these two applications are very special application because the thing we're interested in is only part of speech. However, in some other tasks, our observed variable is actually a speech waveform as a whole. For example, speech synthesis, you want to generate the speech itself. Speech modification, you want to take the speech, modify some part of it, and it still sounds natural. Source separation, where you hear a mixture of speech, and then you try to separate them. Finally, speech enhancement, you observe the speech in noisy environment, try to recover the clean speech. So in these tasks, the observed variable is the speech or mixture of speech itself, and the hidden variable often are interested in reconstructing the speech. So interestingly, there are so many model speech processing tasks that focus on studying the speech waveform as a whole, but a generative model for speech itself is understudied. The existing models are either not probabilistic or very, very coarse. Just assume GMM model or some Gaussian model to be learned from data. So a good probabilistic model for speech is not well studied, and that's why I'm trying to propose a model called the probabilistic acoustic tube, which can potentially be applied to these speech processing tasks. Now, let's look at the model. So now we're talking about the generative model of speech. So it is definitely very useful to take a look at the physical production process of speech. So here is a human speech system. A speech is produced by pushing the air up to the glottal cords, and then the glottal cords vibrates. That modulates the wave into what we call the glottal wave. And the glottal wave goes up to our oral tract and nasal tract, which are called the vocal tract. And the vocal tract modulates the glottal wave into what we hear as speech. So according to previous study on speech, this kind of physical production process can be well approximated by a very simple source filter model, where the glottal vibration is the source and the vocal tract is the filter. Of course, within a very, very short time frame, this vocal tract can be regarded as stable, and therefore the system can be regarded as a linear time invariant filter within this very short time frame. So to build a model for speech decomposes into building a model for source and a model for filter. The model for source first. The model for source really break into two different cases. The first case is the voice case. The voice case is where your glottal cords actually vibrates. And then in 1985, there is a very well studied model called the LF model, which is still very popular. The LF model basically assumes that this is the first order derivative of the glottal wave. The reason why we take a look at the first order derivative is that the radiation at the lips can be modeled as a first order differentiator. So this is the first order derivative according to LF model. It has three phases. The first phase is the derivatives is positive. This phase corresponds to the glottal cord opening. So this is the open phase. And then here, the derivative becomes negative. That corresponds to the glottal cord closing, returning to a closing state. So this is glottal return phase. And afterwards, the glottal cord is completely closed. So this is called the glottal closed phase. And then the LF model parameterizes this process into these 1, 2, 3, 4, 5, 6, 7 variables. And then these variables have implicit constraints, so that reduces to 4 parameters. And then there are further work that further reduces the number of parameters into 1 that is called the glottal tightness. So when you speak very loudly, your glottal cords tend to be very tight. And then if you speak very softly, the glottal cords lax. So this is the voice model we're going to apply. And then for the unvoiced model, unvoiced model is unvoiced case is the case where your glottal cords does not vibrate, like when trying to whisper or taking breathy speech. And then the excitation in this case is basically the very high speed irregular turbulence occurred at the closed part of the glottal cords. And then we simply model this kind of excitation as white noise. So this is the source model. For the filter model, again, no surprise, we're going to use capsule coefficients, because so far, capsule coefficients are very efficient and Gaussian-like parameterization of the vocal tract. So now we have the model for source and the filter, but this is not enough. Why? Because we have to look at one of the most important assumptions of the source filter model is that the vocal tract keeps constant and the glottal vibration is constant within this short time frame. However, even within this short time frame, this does not hold. So let's look at this speech. This is merely a 30 millisecond frame speech. As you can see, for this speech, this is not perfectly periodic. The amplitude is gradually increasing, and if you take a closer look, the pitch is slowly rising. So we can often observe a very significant AM and FM effect in speech. That's why the source filter model is not enough. To model this, we again build some probabilistic assumption. According to Turner and Sahani's work in 2012, that basically assumes that there's an AM chain and the FM chain. Both are a first-order autoregressive process, and then apply some very smart probabilistic assumptions that make it easy to do the inference. So the source, filter, and the AM-FM effect model constitute the whole probabilistic acoustic tube model we're proposing. Basically, we apply probabilistic assumptions to this model, and then, without going to details, the model contains observed variable, which is the complex speech spectrum. So this is, here I want to emphasize that our model is model the complex speech spectrum as a whole, whereas a lot of other speech models only consider amplitude of speech. And then the hidden variables are, as we have already mentioned, pitch, glottal wave, capture coefficients, AM, FM parameters, etc. And then the final model, if you do the derivation, and if you look at the probabilistic assumptions, will become a Gaussian with mean and variance both being a highly nonlinear function of the hidden variable. So this is a one-line summary of the model. Now, the next thing, and Z follows an autoregressive process because assume the hidden variables changes slowly across time. Now, the next question would be, with this model, how do we do the inference? If we have observed a complex speech spectrum, how to do the inference on the hidden variables? Here, given the time limit, I'm not going to the details, but to do the inference is merely trying to get the posterior distribution of the hidden variable conditional on the observed variable. So according to Bayes' rule, it's basically decomposed into this formula, where the denominator, for our case, is very hard to compute. That's why inference becomes a problem for us to study. There are a couple of ways to bypass this problem, and the approach we're going to use is the Monte Carlo approach. Specifically, there are two approaches we have applied in our model, which is the auxiliary particle filter and the Monte Carlo Markov chain. Both of these approaches, if you're not familiar, are merely Monte Carlo approaches. Basically, generate a bunch of samples and possibly weights that follows the posterior distribution of the hidden variable. And then this particle generating process is tractable. So let's look at experiments. So with this inference scheme, we're ready to perform some experiments onto real speech to see how the model can capture the dynamics of hidden variables. The first experiment I'm going to show is the pitch tracking. So pitch tracking basically involves inferring on the F0, named the pitch hidden variable of our model. So we do our experiment on the Edinburgh data set, which come with a very comprehensive label of glottal movement. And then we compare, we evaluate our system using the gross pitch error, that's percentage of frames whose estimates deviate from the true value by more than 20%, and the root mean squared error, that means the root mean squared error of those estimates over the frames that are free of GPE. And then we compare our approach to one of the pitch tracking benchmark, get F0. As you can see, that both systems perform kind of similarly in terms of GPE, while the RMS is a lot better. This is probably because the inference scheme now is still easily tracked in local optima. That's why we are making GPE error, because trying to converge to another optimum point. But once it's in the right place, trying to refine the pitch estimates, that's why it can get a more accurate estimate of hidden F0 variable. Okay. And then the second is speech reconstruction. Speech reconstruction basically involves inferring all the hidden variables from real speech and then put these variables back together to produce real speech to see if this is close to the original observed speech. And then, so let's look at this. This is the reconstruction result of one of the frames. As you can see, without AM/FM tracking, it is already doing a good job, but it fails to track the AM/FM movements of speech. But with AM/FM tracking, you can see the amplitude gradually goes up, and there is a misplace of a pulse here due to the non-perfect periodicity. But here, the pulse plays overlap with each other. And then we calculate SNR of the reconstructed speech versus the original speech and compare with the straight model, which is a very famous model of speech, but which is a very deterministic model. And then you can see that our model achieves 8.79 dB of SNR, whereas the straight model only like negative. This is kind of unfair comparison because the straight model only consider the amplitude spectrum of speech. It does not consider phase. That's why it's kind of the SNR is very low. So finally, let's come to our final discussion. We have proposed a model for speech, and we don't have time to demonstrate all the results, but it has a good potential to be applied to various speech processing tasks by simply doing inference. But the inference is currently the bottleneck of our system. We've tried a bunch of approaches, including map abstraction, Monte Carlo approach, and we're also considering doing a neural network kind of initialization and then further use other approaches to obtain a good estimate. So if you guys have any idea of how to effectively do the inference, you can it's open to discussion. All right, thank you. Because the Monte Carlo approach is currently the best approach we have, but the current Monte Carlo approach is still computationally expensive. You have to generate 1,000 to 5,000, at least 5,000 particles in order to get a robust estimate of the hidden variables, which is already 2,000 times the real-time rate of speech, and then which making 4,000 real-time. No, not 4 parameters. Actually, the total dimension parameter is up to 40. 40, right. So that's really a huge dimension, the curse of dimensionality. Though it does not hold Monte Carlo, it's still very hard.
So yes. I have read your 2012 paper in which you used the hidden Markov model, and you improved based upon that. So okay. This one you presented is Path 2, right?
Yeah. So the hidden model assumption still holds. That's why we have Z follow the autoregressive process.
The problem with the hidden Markov model is discrete across time.
Yeah.
It means how can you achieve kind of AM-FM effect?
Yeah. So you're right. So the AM-FM model is on top of the Path 2. It's basically a kind of a modification to the Path 2 model. And then the modification is that on top of this Markov chain, we assume there's a continuous varying AM-FM on top of this. And then so the AM-FM parameter itself does not follow the Markov process. It's for final granularity, it's per sample base.
Where actually applied in the parameter generation step.
Yeah, right.
Thank you very much.
Thank you.